Okay, so it's my pleasure to introduce Jyoti Dasgupta from ICER. She is currently a postdoctoral fellow here, and she'll speak on classification, reduction, and stability of toric principal bundles. Over to you, Jyoti.
Thank you. First, I would like to thank the organizers for letting me speak here. So today I'm going to talk on classification, reduction, and stability of toric principal bundles. This is based on a joint work with Indranil Biswas, Arijit Dey, Bivas, and Mainak Poddar. So first, let us start with a vector bundle E over X. So over in this any point X here, so the fiber will be a vector space, which I'm denoting by EX. Now we can define another bundle over X, where now the fiber over X is replaced by considering the isomorphisms of EX with CR, assuming that the vector bundle is of rank R. And then we get what is called as a principal GLRC bundle. So more generally, a principal bundle where G is a complex linear algebraic group, then we can define a principal G bundle pi from E to X. So this is a variety E, where we have a right G action on E, and the action is also free, and the projection map is G equivariant. Now we are assuming X to have the trivial G action. And we are also assume that this bundle is locally trivial in the étale topology. So what do you mean by being locally trivial in the étale topology? So that means that for every point X in the base space X, we have a neighborhood U of X inside this X and an étale morphism U prime to U, such that we can restrict our bundle E to U. And when we pull it back via this morphism, then what we get is trivial as a G bundle. So what is a trivial bundle? That means we have a variety X, then for any algebraic group G, we can define the trivial principal bundle. So that's X cross G to X, where the G action on X cross G is given by, so on X it acts trivially and on G it acts by right multiplication. So that's the first example. Another example would be to take an algebraic variety Y, and we have a free right action on Y by a reductive group G. And we also assume that the geometric quotient exists. Then this is an example of a principal G bundle. And again, if we already have a principal G bundle P over X, and we have some morphism Y to X, then we can pull it back. And the pullback bundle over Y is again a principal G bundle. And also seen that principal G bundles will also come from vector bundles. So here we'll talk about toric principal bundles. So these are defined over toric varieties. So let us first recall what are toric varieties. So for us, every variety, we are considering everything is over the complex numbers. So toric variety is a normal variety X, such that we have the complex algebraic torus to be a Zariski dense open subset of the variety. And the natural action of T on itself also extends to an action of T on the variety X. So first, when examples are given by the torus, affine space, projective space, a more non-trivial example will be to consider some line bundles over a toric variety, take the direct sum and projectivize them. We again end up with a toric variety. Or if you blow up a toric variety at an invariant subvariety, the end result is again a toric variety. Now, because of the torus action on this variety, it has nice combinatorial description associated with it. And just to give another combinatorial flavor, here we are considering a toric variety, constructing it from this polytope, which is a convex hull of these 3 points, 0, 0, 1, 0, and 0, 1. So then one can consider this map from C star square to P2. And this map is given by taking T1, T2 and raising it. These monomials are coming for the this is raised to this vertices. So we end up with this map from C squared to P2 by T1, T2 goes to 1, T1, T2. And in fact, the closure of this image of this map is actually the projective space. And in fact, the vertices of this polytope will correspond to the T fixed points in P2. Edges will correspond to the devices, and here it corresponds to the torus. So for us, for simplicity, we'll always consider that our toric varieties are complete and non-singular. Then, in fact, we can write the toric variety as union of affine toric varieties, where each of these affine pieces are isomorphic to n dimension Cn. So assuming that the dimension of X is n. And here the indexing set is over the fixed points under the torus action. And in fact, every X sigma will contain a unique T fixed point. So also torus was a dense subset of X, and that is in fact the open orbit of the torus in X. So the corresponding point of the identity element in torus in the orbit, we are denoting it by X naught. So now one can consider a vector bundle equipped with torus action, and the study of such vector bundles on toric varieties was initiated by Kaneyama and Kliatchko, and that had some remarkable applications. For instance, Kaneyama proved the existence of an equivariant splitting for torus equivariant vector bundles over Pn of rank R, which is less than the dimension of the projective space. Now, this was closely related to the Hartshorne conjecture, which deals with splitting of any rank 2 vector bundle over Pn, where n is more than 7, greater than or equal to 7. And Kliatchko used the stability of toric vector bundles in his proof of Horn's conjecture, which concerns eigenvalues of sums of Hermitian matrices. Now, since principal bundles generalizes vector bundles, so our goal is to study toric principal bundles over toric varieties. So formally, what a toric principal bundle? So now we are considering principal G bundle over a toric variety X. So we have the right hand side of this now, but over the base space, we have a torus action. So if this torus action lifts the torus action on the total space E, and the action commutes with the action of G, then we have a toric principal bundle. So now we want to classify this toric principal bundles over toric varieties. But then the key is to first look at these affine pieces. So we first restrict our attention to this affine piece X sigma, and we call the restriction of the bundle to be E sigma. So then we talk about distinguished sections. So these are sections with behavior under the torus action is determined by some homomorphism T to G. So what is happening that here over Tx, we'll have these 2 points in the fiber S sigma of Tx and T of S sigma X, because our projection map was T equivariant. And because the G action is free transitive on the fiber, so these two will differ by an element of rho sigma T of G. Now, if this happens to be a function of homomorphism of algebraic groups, then this section is a distinguished section. And this result is that this is trivial. Over such X sigma, such a distinguished section will always exist, and that will give a trivialization of affine piece of E restricted to this affine piece. So now, if we already have a distinguished section S sigma and the associated homomorphism is rho sigma, then it translates S sigma dot G is again a distinguished section with associated homomorphism. But how does all the section over affine piece look like? So we classify such things. So now if we have over E sigma, for E sigma, if we have two distinguished sections, S sigma and S sigma prime, and their homomorphisms are rho sigma and rho sigma prime, then we just have to look at fibers over 2 points. One is that point in the open orbit X naught, and another one is the point, the fixed point contained in X sigma. So over X sigma, if they are differing by alpha sigma, then the associated homomorphisms are related by this conjugacy relation. So rho prime sigma is alpha sigma inverse rho sigma T alpha sigma. So there is a typo here. This inverse will not be there, I think. And another extension relation is also there, which involves beta sigma, which is here. So which involves to both of them. So this is giving a classification of distinguished sections over these affine pieces. So now what we define is a collection of some homomorphism together with some elements of G, but how do we get hold of this? So for each affine piece X sigma, we had this section S sigma, and now at the over X naught, they will differ by some element of G that we call as p tau sigma. So consider all this collection of homomorphism rho sigma and collection of elements. So this will satisfy certain conditions. And those conditions are that for each pair of fixed points, we have this function from T. So this is T going to rho tau T p tau sigma rho sigma T inverse. This is a G valued function. Now this will extend to a function over X sigma intersection X tau. And for P sigma sigma is 1G, and there is a co-cycle condition involving this P sigma. So this is this collection we call as admissible collection, and this is something like the transition function from for the principal bundle. Now we can define equivalence relations among them, and they're equivalent if there is they satisfy certain conjugation relations and some extension conditions. I'm not defining them. So the classification theorem is basically that the isomorphism classes of T equivariant principal G bundles on X, they are in one-to-one correspondence with the equivalence classes of admissible collections. So now let us look at description of the equivariant automorphisms of such a toric principal G bundle. So we now look at the fiber over that point corresponding to identity X naught. And then we for each fixed point, we have a distinguished section such that at sigma at X naught is exactly equal to the choice of this point. And we can do that because we have seen that if we have a distinguished section, we can translate it by G. And we already have some because of the existence result. So you can always choose such section. So now we take some T equivariant automorphism and look at the image of this automorphism where it is sending E2. And suppose this is the point, which is again in the fiber of X naught because we are taking T equivariant automorphism. And because of the transitivity of G action, so it will be some of the form E dot G. The claim is this is enough to determine this automorphism. Why is that? Because by continuity of phi and density of the open orbit in X, phi is determined by just the restriction of the phi to the fiber over the open orbit. But again, by T equivariance, the restriction over the open orbit is again determined by the restriction over just the point X naught. But here it is again determined by phi using G equivariance. So what we have shown that if we consider this map from T equivariant automorphisms to G and send any element phi to this phi xi phi, but xi phi is determined by this relation, then this is giving us an injective homomorphism. So what T is a subgroup of G, and what is the image of this one? So what T is basically given by the collection of all such G such that for all fixed points, we have this extension condition. So rho sigma T, G rho sigma T inverse, this extends to X sigma. And if we just restrict our attention to reductive groups, then we have even a nicer description in terms of some parabolic groups. So now in general, we have this inclusion that automorphism group will contain the center and it is contained in the center, but these inequalities can be strict, as can be seen from this particular example. When we are considering the product of this projective space, G is the general linear group and E is the frame bundle associated to the tangent bundle over X, then in fact, this ZG is strictly contained in the automorphism group. Now we will again see a way to relate this automorphism group with the reduction of structure group. But then let us first talk about equivariant reduction of structure group. So we have a closed subgroup H of the complex linear algebraic group G, and we denote the inclusion map from H to G by phi. So then if we have a toric principal H bundle EH over X with the admissible collection rho sigma, p tau sigma, then we can do the associated construction. So we end up with the associated principal G bundle EH cross G over H, and this bundle has admissible collection phi composed rho sigma, phi of p tau sigma. So I mean, if we start with the equivariant principal G bundle EG over X, then it is said to admit an equivariant reduction of structure group to H if there exists a toric principal H bundle EH such that the toric principal G bundle EH cross G over H is equivariantly isomorphic to EG. And in fact, using our classification theorem, we give another description of this reduction of structure group as a combinatorial description in terms of the admissible collections. So in particular, if we restrict our attention to reductive group and consider equivariant Levy reduction, where a Levy subgroup for reductive group is the centralizer in the group of some torus. So as for example, if you consider the linear GLNC, and if you consider this torus, where this is M up to mth position, they're just diagonal matrix, and these are just identity, then we end up with this Levy subgroup CGT, where this is the diagonal, this is any matrix in GL, the appropriate order, and these are all 0. So then what we have shown that EG has an equivariant reduction of structure group to a Levy subgroup H of G if and only if Z naught H is contained in not TEG. So what is Z naught H here? So this is the connected component containing identity of the center of the Levy subgroup H. So in particular, a maximal torus is also a Levy subgroup because it's centralizer itself. So now we can consider splitting of toric principal bundle. So splitting means that EG splits equivariantly if it admits a equivariant reduction of structure group to a torus subgroup of G. So in this context, we have this result, which is if we have an injective homomorphism of reductive groups G to G prime, then if you have a toric principal G bundle EG over X, and we extend the structure group to G prime via this associated construction. So after extension, if the principal G prime bundle is equivariantly split, then the original bundle started with EG, that also splits equivariantly. Now this has an application as an analog, principal bundle analog for Kaneyama's result. So recall that Kaneyama's result talked about the splitting of equivariant vector bundles of rank less than n on projective space of dimension n. So here we are considering reductive subgroup of GLRC, and any toric principal G bundle on Pn will split equivariantly if R is less than n. So we start with such a equivariant principal G bundle EG on Pn. So then, because G is in GLRC, we can construct the associated construction and to end up with a principal GLRC bundle. But then that is equivalent to an equivariant vector bundle of rank R over Pn. But then by Kaneyama's result, that will split equivariantly because R is less than n. Because of the theorem I showed you just now, after extension, this splits. So the original one also splits equivariantly. So we also found another proof which uses certain results of Indranil Biswas and Poddar. Now let me go to the stability part of this talk. So, but before that, let us first understand why would one be interested in studying semi-stability or stability. So one way to look at it is that they come as building blocks of torsion-free sheaves, because for any torsion-free sheaf, there is a canonical increasing filtration by torsion-free sheaves, such that its successive quotient is a semi-stable torsion-free sheaf. And that one is, that filtration is known as a Harder-Nurseman filtration. And on the other hand, for every torsion-free semi-stable sheaf also has a such a filtration by again torsion-free sheaves, and now each successive quotient is a stable sheaf. And this filtration is known as a Jordan-Holder filtration. So in this sense, semi-stable and stable sheaves are building blocks. And on the other hand, there is this fundamental construction in algebraic geometry of moduli spaces, and they arise in connection with classification problems. So you'd like to have a geometric space like variety or scheme, such that the points of that space are in bijective correspondence with certain algebraic geometric objects. Like we can consider smooth projective curves of a fixed genus, or hypersurfaces of fixed degree of some projective space, or stable vector bundles of fixed rank and degree. And in this context also, it is beneficial to if you have some semi-stability or stability assumption here. So now let us define stability of vector bundles formally. So we have a non-singular projective variety X of dimension n by a polarized non-singular projective variety. We mean that H is an L divisor on X. So, and we have another vector bundle E over X. So then we can talk about the degree of the vector bundle with respect to this polarization. So that is just the intersection product of the first Chern class of E with Hn minus 1. And then the slope of E is defined to be the ratio of the degree with the rank. So then one can talk about mu stability or Mumford-Takemoto stability of E. So E is said to be semi-stable if for every coherent subsheaf f of E, such that rank of f is strictly in between 0 and rank of E. The slope of f is less than or equal to slope of E, and it is stable if this inequality is strict. So examples of stable bundles are line bundles. And if you have two semi-stable bundles, then the tensor product is again semi-stable. Dual of a semi-stable bundle is semi-stable, and tangent bundle of projective space is stable. So now if we consider toric vector bundles over toric varieties, then we can define the notion of equivariant stability. So equivariantly semi-stable means that now we assume that with respect to that ample line bundle, we can always assume that it is having an equivariant structure. But instead of considering all coherent subsheaves of E, we can just restrict our attention to equivariant coherent subsheaves with the same rank conditions, and then with the same slope conditions. So the slope of the subsheaf will have to be less than or equal to slope of E. And if the strict inequality is there, then it will be equivariantly stable. So then it is proved by Kuhl for reflexive sheaves, in fact, equivariant reflexive sheaves, and by Biswas, Dey, and Poddar for torsion-free sheaves, that the notion of semi-stability and equivariant semi-stability coincide. So this is helpful in the sense that we already have some nice description of equivariant vector bundle, and it'd be easier to track down equivariant subsheaves of those vector bundles rather than search for all possible subsheaves. So now the goal is to generalize this result for toric principal bundles. But first, let me define what is the notion of stability for toric principal bundles. So just directly define the notion of equivariant stability. So if for every proper parabolic subgroup P of G, and for every equivariant reduction EP of EG over any invariant open subset U of X, such that the complement of the open subset has codimension greater than or equal to 2. And if we have this parabolic subgroup, then for every non-trivial character of this parabolic, which is dominant with respect to some Borel subgroup contained in that parabolic, we consider the associated line bundle EP chi. And if this line bundle has non-positive degree, then we call this to be equivariantly semi-stable. And if it has negative degree, then it is equivariantly stable. So this is the notion of equivariant semi-stability or equivariant stability, but we just remove all the equivariant words from here. We just get the notion of stability or semi-stability for principal bundles, which was defined by Ramanathan. And again, here we have that the notion of stability and equivariant stability coincide here. So just to say another thing is that that the notion of stability, semi-stability and equivariant semi-stability coincide is not very hard to see, because for toric vector bundles, it is a consequence of the uniqueness of Hardan-Ursaman filtration, and analogous thing hold true when we are considering principal bundles. The main thing is to check that it holds also when we are considering stability. So, okay, I will stop here. Thank you.
So let's thank Jyoti for a nice talk. Are there any questions or comments? So in case there are no questions, I can ask, just a few questions. So to clarify some of the things. So maybe you can you explain like what's the significance of this extension conditions, because that seems to be in the first part, classification and so on. Like you mentioned the extension condition, but you didn't say anything about it, sort of why it is needed or something.
Yeah. So this is so maybe I can here, yeah, maybe here it will be. So this admissible collections are something like the transition functions, and so we have a chart which is given by this x sigma, and this is the intersection of two elements there, and because the torus is dense, so here we are saying that just by looking at what is happening over the torus, this extension condition will say that like that is happening over the intersection, like the overlap also that is working. So mainly the density of the torus is playing a role here.
Okay, Jyoti. So in case there are no other questions, let's thank Jyoti again, and thank you.